Hello everyone. Uh, Very good morning. This is Dr. Krishnan, Assistant Professor, Department of Physics, St. Joseph College of Engineering. First, I welcome our patrons, respected Chairman Dr. B. Babu Manoharan sir, our Managing Director Mrs. Jessie Priyama, our Director Mr. B. Shashek sir, our Principal Dr. Vati Shashikri Rao, our Dean Research Dr. B. Parvardhani ma'am, Head of the Department of Science and Convener Dr. V. N. Nandini Devima. Most importantly, I welcome all the participants for this 3 days online faculty development program. A few words related to the first day session before commencing today's session. Nanotechnology is the field of research and innovation concerned with the building things, generally materials and devices, on the scale of atoms and molecules. Nanotechnology has had a profound influence on scientists and technologists, a way of thinking about how a diverse range of technologies will shape up in the future. Nanotechnology research and development is expected to accelerate the success of science and innovation breakthrough towards nanosystems by design to lead many additional and qualitatively new applications by 2020. Guided by social needs, nanotechnology will be translated from the research labs to consumer use, motivated by responsiveness to societal challenges such as sustainability, energy generation, conservation, storage, and conversion, and improved healthcare that is lower cost and more accessible. Today, nanotechnology research and development to develop a coordinated approach to use nanotechnology innovation for the breakthrough solution in sustainable development. In this context, we hope the lecture by our invited speaker, Dr. G. Bhavan Narayana, on nanotechnology for energy harvesting, conservation, and storage will help the audience to acquire a clear picture in this particular domain. So, with this, let me call upon Mr. Khalil Muhammad Ibrahim to give an introduction about the speaker.
Good morning to all the respected dignitaries, staff members, my dear colleagues, and enthusiastic participants. All are welcome to the Faculty Development Program on Recent Trends in Physics, organized by Department of Science, St. Joseph College of Engineering, Chennai. Nanotechnology is a field of research and innovation concerned with the building things generally, materials and devices on the scale of atoms and molecules. Nanotechnology had profound influence of scientists and technologists' way of thinking about how a diverse range of technologies will shape up in the future. Okay. Here, in this context, we hope the lecture by our eminent invited speaker, Dr. G. Bhagwan Narayanan, on nanotechnology for energy harvesting and conservation and storage will help the audience to acquire a clear picture in this particular domain. A good introduction is essential to get a speaker off to a good start. It is my immense pleasure and privilege to introduce our eminent invited speaker, Dr. G. Bhagavan Narayanan. Okay. Professor G. Bhagavan Narayanan, born in Machara, EG district, Andhra Pradesh. Did his MSc from Andhra University and PhD from University of Delhi under the supervision of Professor Tringunyar, Delhi University, and Professor Krishan Lal, ex-director, National Physical Laboratory, Delhi. He served over 32 years as a scientist at various levels, including head of the Department of Sophisticated Analytical Instrument Division at CSIR, National Physical Laboratory, New Delhi. He superannuated from National Physical Laboratory on 31 May 2015 as a chief scientist and a professor and head of crystal growth and X-ray analysis activity. Later, he served as professor in IIIT Nuzwit during May to September 2015, and for about 3 months served as professor in physics, KL University during 16 January 2016 to 12 February 2018. He served as director for IIT RK Valley branch of Rajiv Gandhi University of Knowledge Technologies, Andhra Pradesh. At present, he is working as a Dean Research Honorary VSM Group of Institution, Ramachandrapuram, EG District, Andhra Pradesh. His main research areas are crystal growth of device, quality, non-linear optical and high energy radiation detector, bulk single crystals by solution and melt techniques and characterization of has grown and processed single crystals, epitaxial layers, including hetero, bipolar transistor, and quantum structure, and their devices by various high resolution X-ray diffraction and scattering techniques. So far, he published more than 300 research articles in high impact factor international science journals with over 7,300 citations and 40 H factor. He also published 60 papers in proceedings. Two of his research articles were selected in the top 70 outstanding scientific articles out of 8,000 science articles published by CSIR in 70 years in all areas of research, complied on the auspicious occasion of its 70th year of establishment on September 26, 2012. He has delivered more than 150 research and development and academics invited lectures, keynote plenary lecture, and the chief guest addresses at different prestigious national and international conferences, institutions in the country and abroad. During 2011 to 2015, he was teaching MTech and a PhD students in the newly started Academy of Scientific and Innovative Research program by CSIR. He is a recipient of MRSI, Materials Research Society of India, Best Paper BMS in 1999 Award and a Professor P. Ramasamy National Award 2009 for Crystal Growth from the Indian Association of Crystal Growth. A patent has been granted for the development of a new non-thermal annealing technique for the fabrication of shallow PN junction. Sorry. He developed a state-of-the-level multicrystal X-ray diffractometer and invented two characterization techniques to characterize epitaxial films for determination of relaxation and composition by combined X-ray and Raman method, and to determine the crystallographic orientation of surfaces of single crystal or wafers by high resolution XRD. He established many formal collaborations with various research and development and academic institutes like Anna University, Alapa University, MK University, Bharidasan University, ST Hindu College, Nagargoil, SSN College, Jamia Emilia, VIT University, Vellore, Loyola and Presidency Colleges, Chennai, Government College, Rajamundry, Delhi University, SSPL, Delhi, Lastec, Delhi, RRK, Indur, etc., and guiding many young researchers through his expertise and by giving lectures on different platforms. He has been an invitee for lectures in various national and international conferences. Okay. With this brief introduction, I hand over to the mic to the speaker, Dr. G. Bhagavan Narayan sir. Dear participants, join us providing a hearty welcome to our invited speaker of this FTP programs. Now I request to Dr. G. Bhagavan Narayan sir to carry out the session. Thank you.
Thank you very much for your nice introduction. First, I would like to express my heartfelt thanks to the organizers of this FDP program, and also the authorities of St. Joseph's College of Engineering, Chennai, which is a part of Joseph's group of institutions. I am in particular thankful to Dr. P. Krishnan, who approached me to invite to give a lecture on this auspicious occasion. And with this few remarks, I would like to start my lecture. So this is actually as on today, energy and health sectors are very important for us. And today, for the today's lecture, I have chosen this nanotechnology for energy harvesting, conservation, and storage. Before starting my lecture, I would like to congratulate all the organizers and the St. Joseph's College of Engineering for organizing this workshop, work of a FDP program. And okay, this is the motivation and the outline of my talk are as follows. Nanomaterials are replacing the conventional bulk materials due to their tunable properties when the size is in nanoscale realm, that is with at least one dimension from 1 to 100 nanometer. Due to their high surface energy, reactivity, mechanical strength, quantum confinement, etc., nanoparticles have novel properties and applications. To inspire young researchers and faculty to pursue innovative research in the area of nanoscale science and technology, the following topics are going to be described. With a brief introduction, I will give a some overview on the synthesis of nanoparticles, thin films, and their structures. Of course, recently at RK Valley, that is IIIT RK Valley, I have given this exclusively on this topic with 24 techniques. So actually, this is because of the why I cannot leave this important part is that to start any researcher first one has to do this synthesis of nanomaterials. And for this talk, because my actual talk is different, that is on energy, so I would like to limit the some 16 techniques, and I may go little faster uh, to cover all these aspects. And of course, after that, a brief overview on nanomaterials for their properties and applications will be given. Then nanotechnology for energy harvesting, conservation, and storage. On this, there are 7 topics I will give, and with a summary and conclusions, I will briefly tell all those things. So, sir, is it audible properly? Hello, organizers.
Audible,
Yes, sir.
sir.
Yes, sir.
Audible,
Sir, you
sir,
can
but
proceed, sir.
video is not visible, sir.
It is visible, sir. Visible, sir. You can proceed, sir.
Okay, so my this PPT is also visible in full scale, full screen. Am I right?
Yes, sir. Yes, sir.
Okay, thank you, thank you. If there is any technical mistake happen, please let me know during the lecture also. Okay, so nice. Okay, nice for
Yes,
your
sir.
kind instructions. Okay, so first let us see how small the nano is. The word nano stems from the word nanos, that means dwarf in Greek language, that is small actually, and it is actually 1 billionth of the unit. It is 10 to the power of -9, and nanometer means 10 to the power of -9 meter, and it is the study. Nanoscience is the study of objects with the size between 1 to 100 nanometer, at least in one dimension. May not be in all the 3 dimensions, this thing, but at least in one dimension it should be in the nano region. And nanotechnology is the term used to cover the design, construction, and utilization of functional structures with at least one characteristic dimension in nanometers. Nanotechnology is an emerging technology, deals with the synthesis, processing, and applications of nanomaterials. Let us see practically how small it is. So DNA is 2.5 nanometers, and 1,000 of its size becomes a size of the bacterium, and 1,000 of its bacterium size becomes a size of a raindrop. And in other words, a single carbon nanotube has a diameter of 1 nanometer. 1 lakh of it gives the diameter of the strand of hair, a human hair, and then 1 lakh times will give the 10 meters. That is the equivalent to width of a normal house. So it is so small that when okay, so when the solid material is divided into parts, so its surface area go on increases exponentially. You can see from this graph that you see when the size is reducing in the nanoscale, your fraction of the atoms on the surface go on increases exponentially, and the bulk atoms will go on decrease. They all come on the surface. So like that, it has a surface area is increasing tremendous in a tremendous way, and so because of this so much surface, sorry, so there are non-coordinated broken chemical bonds on the surface. So this actually gives a special properties for this nanostructure. It has some problems also, but it will give a very good properties for this. And these are actually these are also known as dangling bonds. A chemical bond associated with an atom in the surface layer of a solid that does not join the atom with the second atom but extends in the direction of the solid's exterior. That is called dangling bonds. So let us see. Okay. So because of such dangling bonds, the surfaces have a lot of surface energy, and actually to create such broken bonds, we have to do some energy on that. So it will always have at a higher energy. So it will be unstable also in that in that way, because every material will try to be in their least energy state. That is Gibbs free energy. It should be as small as possible for its stability. A simple example is a water droplet. Water droplet. You see, in the it when it is falling, it will be a raindrop. It will be in this shape. But when it is fall on a lotus leaf, it will take the spherical shape. Though the gravitational force tries to flatten it. So how this is actually happening? It will try to make the least possible surface area. So everything will try to become having the least surface area. And similarly, if you melt a crystal solid, it will try to be a spherical shape. It will take a spherical shape. So because we have to do some energy to create some extra surface, it can be defined by this equation, and this is the expression for this surface energy. It depends upon the number of broken bonds, that is dangling bonds, and the surface atomic density, and the half bond length, and the bond strength. So always they are always have a high energy. So okay, because as I told you, so this the surface energy, it will try to be in a minimum value. So therefore, these atoms they may shift inwards, and also a lateral shift is possible, so that this surface energy becomes minimum. And also sometimes it will make bonds with the neighboring atoms, and also it attracts so many other terminal chemical species, and also it can trap some of the molecules, and also it can lead to some physical absorption of various atoms or molecules on the surface. By doing so, it will be relaxed, and it will go to the minimum energy state for its stability. So Now let us see the importance of nanotechnology. Nanotechnology enhances the scope of preparing novel materials whose properties depend upon the particle size, and size-dependent properties of nanomaterials improve their functionality, durability, and reliability. Nanomaterials are replacing the conventional bulk materials due to their tunable properties. The importance is explained based on properties and the applications in the following slides. So first we would have a discussion on this, how we can synthesize various nanoparticles, thin films and their structure for different applications. So when the size of the material approaches nanoscale regime, the surface to volume ratio, surface energy, chemical reactivity, catalytic nature, optical, electrical, electronic, mechanical, magnetic, thermal properties, etc. enhance, and one can tune these properties with size. Very, very important property of these nanomaterials. We can tune their properties with along with their size for novel applications. Various synthesis methods pertaining to nanocrystals, thin films, and their structures are described as per the outline. So we will describe all these things. In total, this will be 19. I will go a bit quicker. So there are two approaches actually to prepare this nanoparticle synthesis. One is the top down. In this, the bulk material um, uh, is crushed or grained into powders, and then they will further made it into nanoparticles further by methods like physical methods like ball milling, etc. In the bottom up approach, we will start with atoms, and then they will form into clusters, and then finally nanoparticles. We will see some techniques actually. In the top-down approach, the particles may not be very uniform, and they may have a irregular shape, and also they may subject to some impurities due to the balls and other things which are supposed to be used in this technique. Whereas in the bottom-up approach, we can get a uniform nanoparticles or nano structures, and they are less prone to impurities, and we can have a better control compared to the top down approach. So let us see. Okay, so even after we prepare these nanomaterials, as we know that they will try to relax, and for their stability we have to do something. So here during the processing steps of devices, they may undergo some centering process, then their surface becomes like this. So these are the domains, and they will change like this. And also there is one natural property of that is Ostwald ripening. So the smaller one, the small nanoparticle will merge into the uh, bigger one, and therefore the properties will change. So, but another thing is there agglomeration of these nanoparticles in this way without changing their independent size. So this has no problem actually. This way we can stabilize these nanomaterials, and there is we can also use surfactants to stabilize these nanoparticles. For example, there are some materials like some materials like phospholipids. They have a hydrophilic head and hydrophobic tail. So these actually, so they will form into missile like this, and some of the materials which are having like some polymers, they may be they may go into center of this missile, and then they will not subject it to further agglomeration like this. So that is, these are called surfactants, and by using such a phospholipids like that, we can stabilize these nanoparticles, and if they are hydrophobic, they will come into the center. And also we can use some core shell structures or double layered structure like cadmium selenide by cadmium selenide, zinc selenide by cadmium selenide, and so on. And also there are some structures like quantum dots also very stable. We will see all those things, and there are varieties of strategies for making these nanomaterials into powders, thin films, and their structures. We will see one after the another. So this is the top-down technique of high energy ball milling. So it is also known as mechanical alloying or crushing for making nanopowders as small as 5 nanometers. So this ball mill contains a hollow cylindrical shell rotating around its axis, uh, which may be either horizontal or at a some angle. Actually, the picture is shown in the vertical way, but it works on the horizontal way, or it may have some slight angle to the horizontal, and it uses a very hard spheres like steel, made up of steel or tungsten carbide balls, and generally for a good results, the mass ratio of the balls to the material is to be should be 2:1 ratio for a better results, and larger the number, smaller the ball size. To prepare smaller nanoparticles, we can use small balls, and the basic principle of this ball milling is impact and aberration. Actually, the size reduction is done by impact as the balls drop from the near top of this shell to this the bottom. And here, actually, there are many varieties, many types of mills, uh, planetary and rod and tumbler, etc. Actually, the energy, the impact energy in this way is 40 times higher than that of the force due to the acceleration gravity. So it gives a lot of impact energy, and it crushes the into nanomaterials. We can use this way also, and this is also for a high energy ball milling. This is also useful, but above a critical speed of this thing, so it is of no use. The speed, because above that, these balls will move along the diameter of this shell. And okay, sometimes we have to use this cryo cooling also, because during this impacts the temperature rise may be from 50 degrees to 1100 degrees centigrade. So therefore it is sometimes it is required to use this cryo cooling also in this ball milling. So the few advantages are like this: few milligrams to several kilograms of nanoparticles can be synthesized using this technique, and inexpensive, old, well-established process, and down to 2 to 20 nanometers are possible. Some of the materials like cobalt, there are metals and some alloys also one can make by this ball milling. And of course, there are some defects and irregular shapes, and this also can be used for the mechanical alloying. And okay, so the very important set of techniques is based on the vapor deposition methods, and again there are two varieties basically: physical vapor deposition and chemical vapor deposition. In both the cases, the material, the source material should be in the form of a vapor, and they will condense on a substrate. And again, this physical vapor deposition, again, there are four varieties, and this last one again consists of three sub varieties. And the chemical vapor deposition, there are three. We'll discuss all these things. So here in the physical vapor deposition, a pure source material is gasified via evaporation with either through thermal evaporation by using the electrical heaters of having with a filament, and by passing a current of 50 to 200 amperes, and we can gasify this source material, and it will deposit on a substrate kept on the top, and slowly the atoms will go on deposited on this. We can make a thin films, and we can also use the electron gun, where these electrons are coming from this gun, and they are directed to this crucible, and then you can focus this electron beam, and because of the heat generated by this collision, it will evaporate, the material evaporates, and then it will deposit on this. And also we can use this laser radiation to eject the atoms, or to evaporate the atoms and condense on this substrate. And we can not only make this thin films, but also you can use nano powders like this. The substrate is kept vertically, and then this can be removed and collected at this bottom tray and through this funnel, and we can grow varieties of things way also. So the other one is the sputtering deposition. In this, actually, some of the gases like argon is used to initiate the sputtering. That is, to maintain the plasma, we have to use such gases. And in this, actually, their energy should be more than that of the binding energy of the target atoms. In this method, the target atoms are bombarded by this argon ions when we apply some voltage across this substrate and the target, and they will they will dislodge these target atoms, and they will deposit it on the substrate, and by we can apply the DC voltage, and in this or some RF sputtering also possible. In this, actually, because of this high oscillating electric field, the electrons in between this target, here the substrate is at the bottom, and it is the sputtering material is kept here, the source material, and the electrons are oscillates very fast, and then they will take out this eject this target atoms, and they will deposit it on the substrate. In this, actually, we can make the quantum dots also by making a very thin films. First, the quantum dots will be made automatically by the process of self-assembly, and we can get the thin films, quantum dots, or any structures by this. And by introducing the magnetic field in both, in addition to this voltages, so the trajectory of the electrons due to Lorentz field will increase, and then the sputtering process will enhance actually, and then we can eject the target atoms, and then the efficiency or the rate of this deposition will be increased depending upon our need. And in the RF sputtering, if you use this instead of argon gas, if you use this oxygen, nitrogen, NH3, etc., we can also make metal oxide like L2O3, nitrates like tin nitrate, and carbides like tungsten carbides, etc. They are also can be used to make this type of metal oxides also. So this is the chemical vapor deposition method. In this, actually, the source material is first vaporized, and then it is added to a carrier gas, and they are injected into this furnace or reaction chamber, and here they will deposit layer by layer, and the substrate is kept at a particular specific temperature depending upon the reactivity of this source and the carrier gas. So they undergo some chemical reaction there, and this carrier gas will, that is volatile actually, it will come out, and it will be evacuated by this pumps, and therefore we can make a very clean the thin films here, and can have a very good control over its thickness, and we can grow from nano layers to the you thickness or nano scale thickness or even millimeter also can grow. And again in this there are varieties. So this is called atomic layer CVD. Here, see, we may suppose if we want to make layers of different layers one after the another, so we can send this cursor, the precursor material of one kind at one time, and then a layer will be formed like this, and this residual gas after reaction will be taken away from the evacuation, and then it is ready for the another layer to grow, and the precursor 2 is added to the carrier gas, and again it will send to the reaction chamber, and like that we can grow layer by layer also with this technique. And one can also grow this metal organic CVD, that's chemical vapor deposition. So here actually the metal, the ions actually are in the form of a organic compound, and more the number of carbon atoms around this metal ion. So its temperature, actually reaction temperature will be lesser. So in this process, 500 degrees is good enough, whereas here it may be 800 to 1000 like that. So we can make these thin films in this MOCVD at quite lower temperatures. And in this, suppose if we want to make indium phosphate layers, we have to take this trimethyl indium and phosphine. So these will undergo the reactions at this substrate, which is kept at a something like 500 degrees centigrade. Then a reaction takes place, and the residual gases will be evacuated, and a pure indium phosphate layer will be formed on this substrate. So we can characterize by this high resolution XRD and the epitaxy methods. And you see, below a particular critical thickness, if you make a thin film, it will be very well matched with the substrate. It will take the exact lattice constant as that of the substrate. So it will very well match this A level. But in doing so, there is an elasticity. If there is a compression here, and there will be elongation in this direction. So by measuring this A perpendicular and A parallel by X-ray methods, you can measure the composition or the thickness in nanometers of any structures like silicon germanium layer on a silicon. So these are actually this substrate peak contains an additional film peak, and this distance is a function of the composition of germanium here, and this fringe width of this beautiful thickness oscillation is a function of the thickness. By using the semi-kinematical method, we can measure this composition and thickness very accurately. And similarly, we have characterized this quantum wells by preparing this molecular metal oxide chemical vapor deposition. That is by these are grown at IIT Kharagpur by Professor D.N. Bose and his group, and we at NPL have characterized the first time in India. They're grown and characterized it first time in India, and we got that paper got an award. It is published in the Bulletin of Material Science for the year 1998. So we can grow and characterize these things, and this is the molecular beam epitaxy technique. In this actually, so there are some separate to heat different materials. We have a separate quasi-Bunsen effusion cells which are here. In this actually we are using very pure materials, and they are kept in separately in different quasi-Kunz and effusion cells, and high vacuum, that is ultra high vacuum, is taken in this chamber. So higher the vacuum, and the higher the mean free path actually. So they won't interact actually while passing in this way towards this substrate. These beams will not interact each other because they are at a high vacuum, no collisions in between. So only they will touch the substrate, then only different materials will be will interact here, and reaction takes place at this substrate. And okay, when we using a electron gun, the electrons will be incident on this substrate at a very grazing incident angle, and few of them, they are constructively interfere, and they will give a Love pattern here, which will with which we can know the quality of the films that are being grown in this technique, and the thickness we can measure by this mass spectrometer. So there is a here this is called, this arrangement is called REED, that is reflection high energy electron diffraction. So this facility generally is there. So we have such MBE technique at NPR. So we have, so we can characterize these such structures which are grown by MBA. So sorry. So these are the advanced LED structures, and here you can see there are quantum wells and the quantum barriers, and different layers are there. 7 repeat layer. This set of layers are repeated 7 times, and there is a substrate, and there is a buffer layer, and there is a protective layer here, and we can get the composition, the thickness, etc. by using the high resolution XRD. You can see that these experimental and simulated curve, they are well matched, and we can get all these parameters very accurately. So if you can compare this, so this is what I was telling. So that is the mean distance that molecule, this is MFP is nothing, mean free path of the molecules that they are going to the substrate. That is the average distance that molecule travel between collision with each other is related to the pressure. At rough vacuum, it is 10 to the power minus 5 mm only, but at medium vacuum, like 10 to the power minus 3, its MFP is 5.1, and when it is a ultra high vacuum, like we have used in the MBE, it is 50 kilometers. So they never touch each other, they won't interact. They will directly go to the substrate, and the reaction takes place only at the substrate, and the required film will be grown. So in this we can have some similarities in the evaporation and sputtering. So the very useful technique actually. So now the synthesis of carbon nanotube. Carbon nanotubes and the quantum dots are a very special examples for the nanomaterials or nanostructures. In this actually there is a furnace, and in this there is a quartz tube, that is a reaction tube here. In this actually the graphite material is kept in a cylindrical way, and the high power laser is used, and they evaporate this graphite into carbon atoms, and they will automatically, by the process of self assembly, they will become sheets like this. They will become this graphene sheets first, and depending upon the way they are actually rolling, they will become a variety of single wall nanotubes, and sometimes they may also become form into multi-wall carbon nanotubes. They may be like this coaxial way, and also the spiral way of nanotubes also can be made. These are 3 varieties, and they have, depending upon their structure, some may have a very good thermal properties, and some may are having very good mechanical properties, and some are having very good electrical properties, which can be used for sensor applications as well. This is another technique, that is spray pyrolysis. In this, actually, the source material in the form of solution is passed through a this nozzle here, and in the uh, outer tube there is one a gas carrier gas is passed with a high pressure. Because of this high pressure, the solution becomes a mist, and then they will they will be coated on a they sprayed on a substrate kept on a heater. So the heating depends upon the reaction that is needed here, and the atomizer also control the amount of the source material that has to be spread on the substrate. So this way we can make these thin films by this very simple technique, and this type of techniques can be adopted in your in even colleges and even small educational institutes. One can use that this type of things. Spray pyrolysis, this is called, and by making the mist, and then we can grow very thin films. And the spray pyrolysis can be easy and cheap, and substrate with complex geometries can be coated and leads to uniform and high quality coatings. Low crystallization temperatures and porosity can be easily tailored. And this is another method, that is laser pyrolysis for nanoparticles and nanofilms. Here again, these reactants are sent from the inner tube, and with a high pressure, and there is a on the from the outer tube there is a confinement to gas. So here actually it is again formed into the mist. Here the source material will become a mist, and this mist is orthogonally interact with this a high power laser beam, which is concentrated at this place, and the reaction takes place here, and the nanoparticles will be made here instantaneously. And we should not keep these nanoparticles here for longer times. So immediately this gas that is injected, or a confinement gas, will take away this just formed nanoparticles into this collection bag through this chimney. And suppose if you make a if you put a substrate, we can make thin films as well, or variety of nano materials can be made. And depending upon the temperature and some reactants added to this reactant gases, one can make different sizes and different thickness of the films, etc., by this technique. And actually here there is no interaction with the reactor chamber walls, and attainment of very fine particles and heating of the target is minimal. And here it is expensive, of course, but we can grow good quality influenced by this technique also. This is another a simple technique one can use in any laboratory. This is by electrodeposition. Here, the metal nanoparticles can be grown with this technique on a metallic electrode. Here, this by the process of electrolysis. So, metal oxide, the material is kept as a uh, electrolysis material, and by applying a alternating voltage here, so um, uh, they will decompose, and they will form as rods, nano rods or nano wires. Because you are using a oscillating voltage here, you will find nano rods or nano wires in this perpendicular to this substrate. And actually, because of this pulsating voltage during this on time, the nanoparticle will grow, in this way. And during this off time, one can use inhibits. Actually, the challenge to make nanoparticles is how to control this size actually. So in this during this off time, you can okay, you can put initially also some inhibits to which will cover this first grown nanorod, and then the further growth on the same rod or wire may not be there, and therefore you can control its size. And the higher the density of the electric field, you can get the high density particles, or with this type of pulse, this nano rods or nano wires can be made from few nanometers to even few millimeter thick layers can also be made by this way. It can be adopted in any laboratory, this also. And the controlling of this voltage in a pulsed way, and also these inhibits can be used to stop the further growth and making a very nanoparticles. The how much thickness or what and the amount of nanoparticle that are deposited can be measured by this Faraday's laws of electrolysis, and with this one can make. This is another technique of spin casting. Is also very simple and very cheap technique, but you can grow varieties of thin films as well as the quantum dots with this technique also. You can adapt in your laboratory, 1 or 2 lakhs, you can get the whole system. So that way you can start this nanotechnology in your own laboratory. So in this actually the material like polymers are dissolved in a suitable solvent, and the solution is poured or sprayed on a uh, on a spinning substrate. It is continuously spin the substrate, and then on this if you pour some this type of solution, and it will, because of the centrifugal force, it will spread across this substrate, and you can get a very uniform thin films. And if you use the drop by drop or layer by layer also, you can grow. And by doing so, depending upon its thickness and the rate of making this fill, you can grow this quantum dots also by the process of self assembly. So this is another technique, that is biosynthesis of nanoparticles using bacteria. Is also known as green nanotechnology. And here the bacteria has a very powerful nature. Actually, in any living organism, including in humans, we have these packets of energies, that is NADH, nicotinamide adenine dinucleotide hydrogen actually. Okay, it is very difficult to pronounce. And okay, so this is a packets of energy available in the living tissues, and this bacteria has a capability to oxidize this thing and create this electrons, and they will reduce um, this metal oxide, and they will make this uh, metal nanoparticles. And the same technique is used in industry also to recover for the recovery of silver. Actually, this some type of bacteria like Pseudomonas stuteri, that is Az259, it can aggregate Az on the cell walls. So the kilograms of Az can be recovered from the ore materials by using this technique. And generally, these are used for the noble metal nanoparticles in this way, and these are found a lot of advantages and applications in the nano medicine, and for many cure, and even to diagnose so many critical diseases like cancer and HIV, like that. These gold and silver nanorods or nanoparticles are needed, and you can make this materials in that way. And this is another method, that is microwave radiation method, says nanoparticles. And here you can actually you can react, you can allow the reaction of the solid materials like zinc and selenium powders. You can take it in a quartz tube, a sealed quartz tube, and just you put it in your microwave oven. Which may be your kitchen microwave oven also is good enough to get this reaction done. And in this, actually at a particular temperature like this, it will decompose, it will reaction takes place on this semiconductor powders. And you can get a nano powders in this way. But here actually the controlling of the size is a very challenging, as I have been telling. So in this case, actually, because of the microwaves, they will heat the substances very quickly. And also, if you switch off this microwave, it can quench the material. So therefore, you can heat the materials. How the microwaves are heating, actually the semiconductors are ionic materials. They have the ions, or they will vibrate, they will try to vibrate with the oscillating electric field, and a friction creates in the collisions, and thereby heating come. So because of that high heating suddenly at each place uniformly, they will be subjected to the chemical reaction. ZNSE will be formed, and then you can get this type of nano particles, very uniform, beautiful nanoparticles, with a very simple technique. We have succeeded in making this ZNSE nanoparticles, and we have characterized by powder XRD and the SEM also. And you see, this is powder XRD is better actually to get this crystallite size, not the particle size. Sometimes this may be higher actually. In the powder XRD, we got this 35 nanometer, whereas with SEM actually we got the size as 50 nanometer. This is more reliable actually. So like that we can. So these are in the nano scale. They are also shown a blue shift, which is good for the many applications. And electrical resistivity was found very high when the compared to the bulk material. When they are in the nano regime, their resistance and structures are actually changing, and they are giving some photo conducting properties also. And like that you can make in a very simple way at your kitchen also. You can make such type of nanoparticles, and you can use for different applications. So this is another method of making these quantum dots by self assembly. You see, we have seen already MBE techniques, MOCVD techniques. We can grow, and also this spray pyrolysis and coating, coating, casting, etc. And these are actually the films are grown first on a crystalline substrate, and these uh, they, due to lattice mismatch, they will they will have some dislocation, and because of the strain, there will be problems. But when the thickness is in a below a critical thickness, and they will not form this type of this dislocation, but to release their strain, they will form some undulations on the film surface, and this will grow, and finally they will form into a very perfect crystalline faceted quantum dots. So these are very useful for the energy, for the absorption of solar energy and so on, which we will discuss now. And this is about the properties. I will go through quickly. So structural and mechanical properties. because of the high surface area, surface free energy, the interatomic spacing decreases in metals and increases in semiconductors, and graphene-like materials are having very strong sp2 bond compared to the sp3 bonds in the diamond. So they are very strong, and at the same time they are lightweight also, because surface area is very high, and their elastic limits are also very high, and they are very flexible, and for reversible deformation takes place, and because of that they can be used in so many applications, which I will tell you. And mechanical deformation of a suspended single wall nanotube leads to a great reduction in conductance. And thermal properties, mechanical melting point decreases and is inversely proportional to the radius of the nanoparticles, and they may get this so-called hydrophobicity. So actually, because the contact, the decreasing particle size decreases the contact angle, and finally this hydrophobicity will increase tremendously, and materials like paints and windows and all those things, one can use this type of nanoparticles for their self cleaning. So the dust will not remain, or even water will not remain like that. It can be used as a self cleaning. And these optical and electronic properties, when electrons and holes squeezed or confined into a dimension that approaches exact and O radius, the energy spectrum becomes um, uh, becomes discrete. It is not continuous like in a solid material, and the band structure will become discrete in nature, like in a atom, in an isolated atom. It will be like this, and lesser the size, higher the band gap energy. So with the same material, if you are changing its size, of course, in a nano regime, you can have different materials, nanoparticles with different band gap energies. So therefore, we can by using the same material or same type of quantum dots with the different sizes, we can use for different applications, like different quantum dots can absorb different energy wavelengths in the different wavelengths in the solar spectrum. So like that, in the liquids, these are also contains some quantum dots here. They are spread in the solution, and because of their size difference, the same material, this is cadmium telluride, same material is giving different colors. And similarly, the gold also you can see in a blue color, depending upon the size of the nanomaterial. You can see here the energy band gap is a okay. This is for the bulk material, and it is D is the diameter of the nanoparticle, and lesser the D, higher this value, and it will be added up. So therefore, this band gap is increasing, and similarly with the optical band gap governed by this equation. And the chemical properties, due to large number of surface atoms, broken or dangling bond, and so on, you can have different properties, like chemical properties like reaction rate. So reduction reactions in electrolysis is very good. Selectivity, and we can have this electrolyte membrane with nanopores, allows to pass only hydrogen, which we'll see in an application. And catalytic activity, target ability, and the transportation ability, solubility, etc., are actually they are different, and these can be used for different applications, including the nanomedicine and the nanobiotechnology. And so they are very good application for this enhanced properties, enhanced chemical properties. And similarly, we can have a super paramagnetism. Suppose a ferromagnetic material in bulk behaves like a in bulk is a paramagnet, some of metal, but when the size is in nano, they show as a paramagnet. And but when you apply the magnetic field, it will become again a paramagnet. So these are called super paramagnetism is called. And similarly, giant magnetoresistance is also possible because these materials have a different bonding in the surface, so they will have a very good different varieties of magnetic properties comes. And in thin films we can find this type of giant magnetoresistance, and this can be used for the data storage and sensing application. And these are different applications. And because of the high strength, because of sp2 strong sp2 bond, they end up of the sp3 bonds in diamond. So and also the lightweight, they are used for the automobile, aeronautics, satellite communication, artificial limbs, etc. And in the medicine, you can the nano machines that can rebuild artists' bones, etc. can be made, and drug delivery is possible with large surface area can attach functional groups and deliver the drug. Cancer treatment, common dots are already invented. They contain fluorescent dyes and identify the tumor cells for early detection. And they have this multiplexing properties for the quantum dots, and they can emit different lights for the same incident wavelength, and they can give the information whether it is even at the very early stages of the disease. And multi-wall carbon nanotubes, they as a good reinforced material. They are used in biomedical bone cement and implant coatings, etc. And environment detecting, they can detect pollutants because of their adsorption through nanopores. Trapping and removal also possible. Cleaning up of pollutants. You see, the nanowire meshes can absorb oil spills 20 times to than that of their weight. They can absorb that much, and at the same time they can reject the water due to hydrophobic nature. So one can clean that such type of pollutant. And conversion of the harmful vapors into harmless gases because of their high catalytic nature. And in the energy or fuel, we will discuss in detail. That is the today's topic actually. So food and agriculture also, they have lot of application. There are sensors which change the colors when the food is spoiled, which can tell can help the customer. And sensors like quantum dots, DNA mono sensor, uh, such type of applications are there. And electromagnetic sensor, electrochemical sensor also there, because when there is a slight the force is applied, their structure changes and their resistance increases like anything. So that can be used as a sensor. And similarly, one can use these nanomaterials as nano electronics. Like already a quantum dot or a single electrons and transistors have been invented, and so the present microelectronics chip technology will become nano nanotechnology. And one can use the tunneling property of various nano particles which are deposited on a boron nitrate films, sorry, nanotubes, which are insulated. On this, actually, without even touch, they quantum mechanically they pass on the current as a superconductor. So such type of things are very minute volume it requires, and therefore electronics is can be possible. And we have already seen giant magnetoresistance can be used to data for data storage and sensing. So they, like this, in all varieties of science and engineering, one can use the this nanotechnology for various applications. Now let us come to the actually today's talk. So I hope still good time. So one by one, I will cover these things. So this is a example of a fuel cell. So you see here, there are some proton exchange membrane here, which are made up of the carbon nanowires. So they have a particular pore size, and they allow only hydrogen proton, that is H plus ion proton only through them, and they are compelled to pass the electrons through through the load where it delivers the power, and at the other electrode. So these holes and electrons merge with the oxygen, it will give a water, and it will send it in ready for the next pulse, and it will deliver the power to this. And similarly, in the batteries, one can use this nano rods and nano wires. They can be used for the a good storage of the charge, and also because of the high high conductance of these wires, they can be easily charged, and one can use at a very low potential also. So this is one good example, and these are the dye sensitized solar cells. So in this actually, there is a these dyes are there actually, optically sensor. These are optical sensors. They absorb very efficiently the sunlight, and these dyes are coated on a high band gap energy TiO2 type of nanoparticles, and these are coated on these nanoparticles. These dyes are coated, and these are in turn coated on a conducting glass, and which are transparent to the light, and it is having a good conductance for the electricity also. So therefore, these can be used as a photo sensors, like these dyes are used as a photo sensor, and the electron hole pair will be generated with this, and these electrons are simply percolated through the conduction band of this TiO2, that is high band gap semiconductor, and they are transferred to this optically transparent and electrically conducting glass material, and the electrons will flow through the load where it delivers the power, and then it will come back. The electrons will come back to the electrolyte, where it again neutralize your dyes, and thereby one can generate the electricity by using the solar radiation. And this is one technique, and the energy level diagram is like this. And here you can see this after exposing this to the sunlight, so the electron holes will be released, and the electrons are simply percolated in the conduction band of the TiO2 nanoparticles, which are coated on a glass material, and these are transferred to this electrode, and the electrons will go to the load where they will deliver the power, and they will come back in the electrol. In the reduction reaction, the electrons are again given to this. In this process, the recombination of these dyes should not be faster than the reaction, than the electron transportation, so that the efficiency will remain. So this another technique is the quantum dot sensitized solar cells. Here, the quantum dots are used as a photo absorbing material. They are very efficient to absorb the sunlight, and they have a additional character in the classical p-n junction, etc. For one photon, it may be of very high energy. Only one electron hole pair will be generated, but here, because of this discrete nature of the this energy levels, even this high energy photon also will, there is no wastage in the form of heat. It will generate two pairs of electrons, so thereby the efficiency of the cell will increases. This is called multiple exciton generation. So when the size is in the nano, the electronic structure becomes a this a discrete nature, and therefore this type of multiple exciton of the charge carrier takes place, that is electron and holes will generate, and that will enhance the efficiency of the cell. So actually here as I told you, this band gap energy decreases increases when the size decreases. So therefore, in the actually in this multi-junction solar cells, we have to use different materials of different thicknesses to receive all the wavelengths that are coming from the solar spectrum. But here, then the very costly technology and also the costly materials restricts the commercial usage of this multi-junction solar gels, which, though they are very efficient, but here we can use very simple method like this spin casting, etc. And actually, the concentrated nanoparticle solution stabilized by long hydrocarbon ligands that keep the nanocrystal suspended in solution are prepared first. The solutions are then spin coated on a metal oxide semiconductor and then cast down. So in this various thickness layers can be made first, and they will be converted into different sizes of the quantum dot by the process of self assembly. By the process of self assembly. If once these are cast down, then this long hydrocarbon ligands will become short chain cross linker, and a stable quantum structures will be made here. And of course there are some other methods also, successive ionic layer absorption reaction, that is SILAR, and also sometimes there is another electrophoretic deposition also there. And these are bit costly, but as I told you, the spin casting is a very useful technique. You can start in your laboratory with 1 or 2 lakhs of equipment, and you can grow this type of quantum dots, and which are useful for these actually different sizes of the quantum dots will receive different wavelengths and convert all the maximum range of the solar spectrum to give a more efficient output. Actually, there is a natural advantage. The photons of higher wavelength will not be absorbed by these small nanoparticles. They will come to their respective bigger nanoparticles, so that all the wavelengths will be reached to their respective quantum dots and they will absorb, so that the efficiency will increase for these things. And of course, there are ohmic contacts, then anti-reflection coatings, and then the connecting glass sheets, etc. For the normal cell is required. You see here, one for getting a stable quantum dots, one can use this cadmium sulfide, cadmium selenide, and also the core shell structures like cadmium selenide, bicadmium tellurate, and so on. And also one can use this passivation to avoid the recombination. Actually, one should have, there can be some recombination, and which is detrimental to the efficiency of the solar cells. So one can passivate the electrodes as well as the this nano layers, that is TiO2 layer, and also this layer of dice, etc. And so this how it works, we can see like this. You see, this is a connecting glass. The photons are reaching this dice, and the electron hole pair are creating here, and they will simply percolate through the connection band of the TiO2, and they will reach the connecting glass electrode, and they will give the electrons to the load, and again they will come back to this in the electrolyte, and by the process of the reduction, again these dyes are replenished by this electron and ready for the to receive the next photon. So like that this works, and it is very efficient and simple. And in the recent advancements are there in this actually surface to interface passivation of quantum dots, and core shell QDs are being used, and because of that recombination at each phase will be very less, and the charge separation also will be maintained. You see, charge separation is very much needed, so this is happening by the interfaces at the quantum dot to the semiconductor nano layer, and nano layer to the electrolyte. So like that, and the efficiency can be calculated by this P maximum. This is the I versus the voltage, and there is a point here where you can get the IM and VM maximum. So this divided by the input light to 100%, and there is an important factor that is called fill factor. So to assess the quality of a particular quantum dot solar cell, that is actually this P maximum is divided by the short circuit current and the open voltage. So if it is around zero 0.8, so you can get a good efficiency solar cell. And there are a lot of advantages over the conventional PN junction, thin films, and the multi-junction solar cell. Favorable power to weight ratio, high absorption coefficient of QDs, and high efficiency due to multiple exciton generation, tunable or size dependent band gap due to quantum confinement, mass and area savings as well as flexibility leads to miniaturization, low power consumption, versatility due to easy manufacturing processes, increased electrical performance at low production cost. It can be used in complete buildings, including windows and not simply the rooftops. And of course, there are some drawbacks. Degradation due to this UV conditions is one thing actually, and toxicity of some of the quantum dots also there, and the shells can alter optical properties, and it is hard to control the size of the particle. These are, but with the recent advancement, these can be improved, and the future scope is very high. Designing new semiconductors with large wavelength range of optical absorption in terms of the quantum confinement, porosity, reducing the threshold voltage, and so on. There are a lot of future scopes for this, and this is a very from the last 5 to 6 years only. This type of perovskite solar cells are being developed, and these are again can be made by the simple techniques like spin casting, etc. And because these are having actually the strong ionic interactions are there, and also one can tune this band gap from 1.5 to 2.3 by changing this perovskite halides actually. So this iron, bromide, or chlorine, we can change, and by changing their composition also, one can change this band gap energy, so that we can get quantum dots of different band gap energies, so that the maximum range of the solar spectrum can be absorbed and can be converted into electricity. And the construction is the same like our QDSS quantum dot sensitizer solar cell. Here the quantum dots are made by this perovskite cells, quantum dots, and they are having very high efficiency, and in within 5 to 6 years they reach the maximum possible conversion efficiencies, which are compatible with the multi-junction solar cells or silicon PN junction solar cells. And this is another method of producing the fuel. The wonderful fuel of hydrogen is also part of energy. So here we are mimicking the nature, that is the artificial photosynthesis. Actually, there is a triad assembly here. In this, there is one photosensitizer, and these are coupled tandemly with a the water splitting agent, and here a catalyst, and another one is a hydrogen evolving catalyst here. So here this photosensitizer, when it is exposed to the light, it emits the electrons to this A catalyst, and it will remain for quite some time as a excited state. So in the presence of such excited state, for example, +2 and all, this catalyst will become very active, and then it can split the water into oxygen and the hydrogen, that is proton. So these protons will directly go to this hydrogen evolving catalyst, where these electrons which are coming from this P, that is photosensitizer, will be reduced, and then you will get a hydrogen. Here you are getting oxygen, here you are getting hydrogen. Both can be used as a fuels, and need a good good quality catalyst and a photosensitizer. Lot of research is going on in this all these things, and particularly the photosensitizer. So ruthenium polypyridine complexes are have been invented. They have a long life, actually excited state, and they can help in receiving the maximum photons and convert into electricity. And there are other, for the charge separation, it is better to use carbon nanotubes, which is a key factor in any solar, in any junction, in any solar cell. And by using this nano tubes, we can do this charge separation. And also these are suffering from this photo damage, because these cells are continuously irradiated by the light, and including the ultraviolet light. So this can be avoided, just like this green leaves are protected by this some bacteria. So we can use such bacteria, that is bio-inspired photo protectants. These are bacteria, actually carotenoids. This is one type of bacteria which are which these green leaves are using. We can also use this thing, and we can reduce the photo damage for their durability and their long life. So one can, there are a lot of research is going on in this catalyst as well as this photosensitizers and other component. And this is actually conservation of energy is as good as generation of energy. So this can be achieved by advanced light emitting diodes. You see, in average, the family for their house, their bill cost around 25%, and for the what they are using for the lighting. And suppose if we are using incandescent bulb, 90% of that power is going waste as a heat, actually. So by using this CFL bulb, that is compact fluorescent lights, so we can save 1/3 to 1/5 of the electricity by using these things. And this is can be further saved by using these LEDs, and it may be compared to this, it can be 1/30th, and compared to this it can be 1/10 of the power saving. So and there are many other advantages for these LEDs. These are the solid material, and its durability is very high, and there is no mercury coating like this CFL bulbs are there. Here there is no harm for the environment, and the most importantly, they consume very little electricity, that is 2 to 17 watts is good enough. and they are lightweight. We can and because of this very low power requirement, they can be used as isolated places or while traveling by just taking some low power batteries. One can use at isolated places and for lighting purposes. And this type of LEDs, advanced LEDs, as I already mentioned, we have characterized it NPL. They are having different quantum wells and quantum barriers, and they may have such 7 layers in this, and there is a protection layer. If once the technology is improved, and we will have a very high efficient LEDs. Already we are using a lot in the market, and some more the power conversion efficiency is going to be improved by using this advanced LED structures. And so our power consumption towards the lighting will be reduced even further, and these are very cheap also. And because we are billions of such products are needed, so therefore the cost per each item will be reduced like anything. And this is about the supercapacitors. So you can store a lot of energy by these supercapacitor. These are resembles two ordinary capacitors which are like, connected seriously side by side actually. And here actually we are putting a insulation thin sheet actually, so that to increase the charging capacity of the capacitor. So that is actually basic principle of a supercapacitor. By introducing the thin insulation layer, we are increasing the charge capacity. But suppose on both the electrodes, if you use this carbon nanotubes, their charge storage can be increased like anything. So it can be uh, very high actually. So in this way, you can drastically improve the power density up to 30 kilowatt per kg compared to the commercial these batteries of 4 kilowatt per kg. So nanotechnology has given a tremendous advantage uh, to uh, to store the power in a very less weight devices, and so that one can use the nanotechnology for good storage of energy as well. So okay, this is actually I'm not going to cover here. This is actually for the health security. So it takes again 1.5 hours time. It maybe in some other occasion I can give this lecture also. This is a this health as well as the energy are the need of the hour. So both can be fulfilled by this nanotechnology, and we have tremendous applications in both even in environment protection also. This nanotechnology can be useful. So this I will give you at some other occasion. Actually, the my intention to give this much lengthy lecture is to inspire the young students and also the young researchers, including the faculty, to come into this nanotechnology research. Any material scientist can come into this, including this health sector, and they can really do a lot of research in this, and they can help our medical doctors, and we can find very good solutions, including for this COVID-19, etc. So this is the need of the hour. So this lecture I may give at some other occasion. Okay, so let us summarize what we have learned. So within the nanoscale region, we can design and construct novel materials for different novel applications by tuning the size and shape like quantum dots, nano rods, carbon nanotubes, thin films, etc. a few applications with respect to their property, shape, and size are mentioned below. Due to large number of atoms on the surface, reactivity of nanoparticles is very high and can identify, attract, and accommodate various functional groups, and hence one can use nanoparticles for applications like drug delivery, medical treatment, and imaging. Early detection of cancer and HIV is possible with such materials, and one can also use this nano material for the biosensors, DNA sensor, for example. And due to discussed nature of the energy spectrum of nanoparticles, when their size is close to that of the Bohr exciton radius, optical and electronic properties can be tuned. For example, quantum tunneling effect can be used to develop electronics like single electron or quantum dot transistors and nanotubes or rods as high conducting wires, which may have 1000 times to that of the conventional conductors, and due to dangling bonds for the surface atoms, they magnetically couple to their neighbor atoms in a different way and possess novel magnetic properties like giant magnetoresistance in multi-layer thin films useful for data storage and memory devices. Due to enhanced mechanical strength, example stronger sp2 bonds in carbon nanotubes than sp3 bonds in diamond, with lightweight novel materials like nanocomposites, nanotubes, etc. can be used for artificial limbs, aeronautics, automobiles, aircrafts, etc. For energy harvesting, we can use quantum dot solar cells with different sizes to absorb all wavelengths of solar spectrum to reduce the manufacturing cost and to enhance the efficiency by multiple excitations. For environment protection, nanometers can detect, trap, separate out the pollutants. Thereby, we can protect the environment. And these are also scientists are used to purify water also through their nanopores, and we can use this in as a proton exchange membranes also, what we have seen in the fuel cells. So like that we have lot of applications, and any physicist or chemist or material scientist can enter into this novel technology, and they can do a lot in the medical science or this nano biochemistry, as well as this energy harvesting and conservation and storage also. Of course, they have some hazards also. Nanoparticles can get into the body directly through the skin, lungs, and digestive system, and indirectly through environment like water bodies, animals, and may pose health problems like nano TaO2 has a photocatalytic effect, that is under UV radiation, reactive oxygen species develop that can damage the cell membrane of our human tissues or microorganisms. Silver nanoparticles or even gold nanoparticles are highly toxic to microorganisms such as bacteria, fungi, and algae. So for environment, there is a little concern. Of course, lot of research has to be done in this angle also to really know whether this will give some hazards to hazards to the human body or the nature. So because the bodies can adapt for so many ill effects of also. So let us see. Let us also now prove that there may not be such high hazards about these nanoparticles, but they can use for many applications. We can make nano machines even to to get some of the to build some of the body parts also. It is possible. And okay, as for nanotechnology can play a great role for energy harvesting, conservation, and storage. And in health security also, nanotechnology can play an important role, particularly in drug delivery, targeting, diagnosis, or imaging. And the message is there is a good scope for the researchers in material science and engineering towards nanoscience and technology. So encash it now. This is particularly for the young researchers, so they can do a lot in this nanotechnology or nanomedicine or nano energy materials. And okay, today we have discussed this how this energy security can be achieved by this nanotechnology. This I have given some 8 years back, Vellore or somewhere. So again giving, I am very happy to be here. So it is, I am very proud to show this type of slides. I am very fortunate that I have so many collaborators, and which they are belongs to great institute, and these are some of them. And for that, one of the organizers, Dr. P. Krishna, when he was doing his PhD in Presidency College, he also we worked together to get some good papers in crystal growth. So like that, there are so many institutes are involved, and these are a few collaborators at NPL, and these are a few students that directly work under me. And there is one currently one part-time registrar is also working. He is a assistant professor at Reply in News Video. He is Durga Babu in the RGPT. So some of the main collaborators are listed from outside NPL. So huge numbers actually. So I'm very fortunate to have such a good numbers. I am thankful to all of them, and to inspire me, and to collaborate me, and help me in various stages. And I also wish some of the students who worked under me, maybe as a collaborator or a PhD, they are all very well settled, and they are occupying very respectable places at different institutes, not only in India but also in abroad. And I am proud to have such a good number of collaborators and good quality people. And now our current situation is like a watermelon. If you open the green zone, it will become red. So stay home, stay safe unless until you have a emergency situation to go outside. So these webinars are very nice actually at this juncture, and we the senior people are very much enjoying. So we are able to disseminate the knowledge to the youngsters by this webinars. So I hope this will go on continue. And thanks for your kind attention. Now, with the due permission of the organizers, I am ready to answer any questions. I will be glad to answer questions for the participants. Hello, sir. Oh, okay, good.
Thank you, sir. Thank you so
So,
much. Thank you so much, sir, for your informative and valuable
okay, good.
presentation, sir.
Okay,
Let me share some
okay,
of the
please.
questions, sir. Can you answer, sir? Before that, I request all the participants kindly post your questions in chat box so that sir can answer. Sir, this is a question from Neeraj Mishra. How can I synthesize nanoparticles of
Okay,
different
as I
shapes?
told, actually some 16 techniques I have described. Actually, you see, in the for example, you want to make nanotubes, you can use this laser evaporation, and actually these are when the graphite material is decomposed into nano, this carbon atoms first, and these are automatically, because of their very strong covalent bond, they will form into hexagonal structure, and graphene sheets will be formed first. And automatically, depending upon the this uh, actually reactants or dopants present in the carbon nanorod, so you can get single wall carbon nanotubes of different diameters and different lengths. And also you can, by using different temperature, ambience and the reactants in the chamber, you can also make the multi-wall carbon nanotubes. And similarly, you can grow thin films, or you can grow nanorods or nanowires, depending upon the conditions that are prevailed in your technique and in your reacting furnace actually. So different these are having different shapes and sizes, and therefore we have to use variety of techniques. That is why I have given a good number of techniques in this lecture, though it is not directly related to my actual topic. So I have covered variety of techniques, 16 techniques in this present talk, and using different techniques, one can use different size and shape of the nanomaterials. So the conditions, the ambience, the reactants, and the method all depends on their shape and sizes. Is that okay? Okay.
Yes, sir. Thank you, sir. So another question, sir. Another question, by Subhash Chandra Bose Prabhu. How can we prepare sphere structured material like
Metal
metal
oxides. Hello. Hello.
Yes.
Okay. So
Yes,
spheres
sir.
are very easy to
Yes, sir.
actually fabricate. As I told you, the nanoparticles will try to become a sphere because the surface area is the minimum for a given volume of the material. The surface energy will be minimum when it is in the shape of a the sphere. So naturally, when you are making these nanoparticles, for example, microwave irradiation or even hydrothermal process, etc., they will form. They form into first spheres only. The spheres very easily. Only to make the rods, etc., you have to use a pulsating voltage like in a electrolysis, electrolysis, etc. You have to use different techniques, and which are difficult for making the carbon rods or carbon nanotubes or carbon wires or a quantum dots. But spheres are very easy. Even by ball milling also, generally you will get a sphere type nanoparticles. So in the chemical vapor deposition or in the this physical vapor deposition also, you can get mostly this spherical type of nanoparticle. So that is not a actually tedious job to get a spherical material.
Thank
Next.
you. Thank you, sir. The next question is by Mohammad Yashin Dawlat. Can nanoparticles be made hydrophilic? If possible, what is the composition
Yes,
of material should
we
be there?
can make hydro. Actually, there are some hydro phosphophilic materials are there. They have a hydrophilic head and a hydrophobic tail. Okay, so these can be used to dissolve any material, uh, and you can encapsulate any material, and whether your source material is hydrophobic or hydrophilic, it hardly matters. So these can carry and they can use as a surfactant. Actually, to make your material as a hydrophobic or hydrophilic, you may add this type of surfactant so that your material also can get this type of properties. Okay, you want? Okay.
Yes, sir. Yes, sir. Thank you. Yes. Sir, next question, sir, by Ramesh Babu. How can I prepare nano glass? Generally, glass is amorphous and nano is crystalline. So how
Nano glasses
glass is
actually
preferred?
nowadays by that spin casting technique, so they are making some solutions actually that is called sol. Actually, these contains suspended particles of even glass material also. They they form with some cross linking, so they are very stable in the liquid form also. So such sol can be deposited by spin coating techniques like that, and then they can cast or dry, they can dry, and then you can have a very glass layers, very thin layers. You can use for a windows and all those things. This glass layers, even in the specs also, you can use such type of glassy materials, and it is possible actually by such techniques.
Yes, sir. Yes, thank you, sir. Sir,
You
one
can
more question,
ask
sir.
as
Last
many
question,
as
sir.
possible. This is the nice
Yes,
part of
yes, sir.
any lecture actually, because the candidates may have different questions. By listening the lecture they may get some doubts, and also they may have some doubts while they are doing research, and they may have some doubts. They can also ask, they can ask in the crystal growth also, or some other. Okay, so
Yes, sir.
I try to encourage all the,
Yes, sir.
particularly the young participants, to ask as many questions as possible. They can even upload their questions even now also. Sir, please ask the question. Next question.
Yes, sir. Sir, next question by Ram Kobar. How can we control the shape of nanoparticles such as rod-shaped or spherical in the
Okay,
salvo-thermal method?
actually in salvo-thermal technique, in fact, we don't have much control on that. Actually, in the thermal technique, actually, which has not covered due to lack of time actually here. So the crystalline phases, actually these nanoparticles are also actually small crystallites. They are not amorphous material. So actually in the salvo thermal process, generally those materials are, they are in their crystalline phases are very unstable at their melting points. So therefore, by using the high pressure in this in this bomb that is called cells actually, so they were under high pressure. By reducing their melting point, we are making this nanoparticles. But in fact they are crystalline phases actually. Different crystallites will be formed in the salvo-thermal method. So we don't have much control on this. Maybe very few articles may be there. By using some inhibits or the surfactants, so which can be used in this technique also, they can control their size, and also they may try to regulate their shapes also. But to the best of my knowledge, it is very difficult to control in this method. You can choose other methods. You can choose other
Yes, sir.
methods
Thank you.
like electrolysis. In that, actually, rod type of nanoparticles can be made by using pulsated, by applying the pulsated voltage to the electrodes of the this cell. Okay, and sometimes you can use this laser pyrolysis, etc. You can use a pulsating laser to make rods or wires type of things. Of course, in the special technique of carbon nanotubes, you can make these tubes also. Okay, next.
Yes, yes, sir. Thank you, sir. Thank you, sir.
Yes.
Already we are running out of time, sir. Yes. So I have no words to express my thanks to Professor Bhagavan Narayana, sir, because he helped me a lot, not only for me, like my researchers. As a part of this FDP, let me call upon Mr. Khalil Muhammad Ibrahim
Thank you.
to deliver a vote of
If
thanks.
you want to turn your life around, try thankfulness. Gratitude is the way of appreciation. Hence, I would like to thank the respected chairman, Dr. B. Baba Monogaran, our managing director, Mr. S. Jessipriya, the director, Mr. G. Sasisekhar, principal, Dr. Vati Sesagre Rao, Dean Research, Dr. B. Parvadavati, and our head of the department and convener of this program, Dr. V. N. Nandini Devi. And we also would like to acknowledge our gratitude to the resource person of this day, Professor Dr. G. Bhagwan Narayan sir, for exposing his theory very elaborate way. He clarified and explained everything about nanotechnology as a frontier. Thank you very much, sir. I am happy to express my thanks to my organizing team and the department staff members for their blessings and support. Also, I would like to extend my deepest gratitude to all the participants for their interest to attend the FTP and made this a
Okay, thank you very much for giving me enough time and
grand success.
listening my lecture very patiently. I am thankful to all the audience also. So if there is any other chance, I am ready to give other lecture also. That is a health security. So this was it. So,
Yes, sir. Thank you, sir. Thank you so much, sir, for your valuable time and presentation, sir. I request all the participants kindly fill the feedback form. We'll say end the session in another 5 minutes. Thank you, all the
Thank you, sir.
participants.
okay, bye.
Thank you so much.
Thank
Sir.
you.
Dear participants, kindly fill the feedback form, and tomorrow we can start the session by 11 o'clock.
Okay, bye.
Participants, kindly fill the feedback form. Let me end the session.